Physicists love talking about anomalies and tensions in their data because every such tension could mean new physics. In cosmology, we've had the Hubble tension that has attracted a lot of attention in the past decade. It might just have disappeared. Let's have a look. The universe expands. You have probably heard of this. But how can we possibly know that the universe expands? We can't see what galaxies are doing a billion light years away from us because it'd take a billion years until we can see it, and no one wants to wait that long for a YouTube video. Indeed, we can't measure that the universe is expanding right now. What we do is we look at distant galaxies, and because the light takes so long to reach us, we see them as they were in the past. And from that, we calculate how the universe should be expanding today according to Einstein's equations. The rate at which the universe is expanding is known as the Hubble rate, denoted with a capital H, and the rate at which it's expanding today is h0. The issue is now that cosmologists have used different measurements to determine this constant h0 and got different results. This is the so-called Hubble tension. The discrepancy is not huge, but the measurements are outside each other's uncertainty range. There have been many different measurements by now, but the ones that have the biggest discrepancy are those using data from the cosmic microwave background and those from supernovae. There are 4 possible explanations for tensions like this. The first one is that it's some sort of measurement error with one or the other experiment. Indeed, this is what physicists thought when this tension first arose, but by now they've double and triple checked everything, and that seems now a very unlikely explanation. The next possible explanation is that it's an issue with the data analysis. The third is that it's a problem with the model, and the fourth is a problem with the theory. You might be confused because I'm distinguishing between model and theory, so let me explain. The theory is the overarching mathematical framework. In the case of cosmology, that's the field equations of Einstein's general relativity. But just how you use these equations depends on what it is that you want to describe with them. You might be looking at a black hole, in which case you use a black hole solution, maybe one with gas around it. Or you might be looking at a spiral galaxy, in which case you might use a disk with a bulge and a halo and so on. If you're looking at the universe as a whole, you normally assume that matter and energy in the universe is on average distributed the same everywhere. This is a model for the universe, not a theory, because it requires extra assumptions about what is inside the universe and how much of it and how it's distributed. The model which physicists currently use for the universe is called lambda CDM, where the lambda is dark energy and CDM is cold dark matter. It's also sometimes called the concordance model or the standard model of cosmology. That said, let's come back to the Hubble tension. The most exciting possibility would be that something's wrong with Einstein's theory. But before you throw out the entire theory, you try to amend the model. Indeed, in the past years, the most popular explanation for the Hubble tension has become that dark energy changes in time. That'd be a change in the model, but it'd still be Einstein's theory. I lost interest in this Hubble tension a few years ago after I talked to Zubair Zarkar, who convinced me that there's something very wrong with the supernova data analysis. The new study now seems to indirectly support what Zubair told me all these years ago. It comes from the group of Wendy Friedman at the University of Chicago. They wrote a paper about this a few months ago, but now just reported an update at the recent APS meeting in Sacramento. They used data from the James Webb Telescope for 2 types of stars, the Cepheid stars and red giants. It's a little more difficult to extract information about the expansion rate from these stars than from supernovae, but the excellent data quality from the Webb telescope makes it possible. The result they get agrees with that of the cosmic microwave background. All of this fits neatly with the suspicion that there's something wrong with the supernovae analysis. Now, one way to look at this is is that this is a boring story of a tension gone away. But I think this isn't quite the end of the story. For one thing, there'll almost certainly be other physicists questioning the results of the Friedman group. But more importantly, when it turns out that there's indeed something fishy with the supernovae analysis, then there'll be a lot of other studies that'll have to be redone too. I want to remind you that the supernovae data was the key factor for handing out the Physics Nobel of 2011. So I'm pretty sure we'll hear more about this. Stay tuned. Dyson spheres are hypothetical megastructures built by highly advanced civilizations around their stars to harness energy. A group of astrophysicists says they've identified several possible candidates. Now you might say, go away, that's just one of those crazy alien stories. But I'm hoping to convince you that this isn't as crazy as it sounds. A Dyson sphere is basically a giant power plant that wraps around an entire star. The inside of the sphere would be covered in whatever the aliens call their super-duper version of solar panels. That grabs off the energy, and if you want visible light on your planet, you can use that energy to create it where you need it. Dyson spheres are named after the physicist and mathematician Freeman Dyson, who came up with the idea in 1960. Compared to normal stars, such structures would appear unnaturally dim in the visible range. But since they'll inevitably get warm when they harvest all that energy, they'd still emit waste heat in the infrared. There isn't any type of star that we know of that naturally looks like this. A group of astrophysicists has now identified 7 possible candidates whose emission characteristics look like Dyson spheres. They could just be weird stars or stars covered by dust or something else, like maybe giant hot potatoes, but maybe they're the real thing. These candidate objects will now be investigated further. I don't think this is a crazy idea for the following reason. Technological progress is strongly tied to energy access. We know this from all civilizations that we've ever looked at. The more advanced, the more energy they use. This is basically why I think degrowthers are enemies of humanity, but I digress. Now, we hear a lot of talk about how we're not using all that wonderful solar energy that reaches us every day from our magnificent sun. If we covered the entire surface of our planet with solar panels, that'd deliver several thousand times the current global power consumption. But most of the energy from the sun never reaches us in the first place. It goes into outer space. Such a waste. If we covered up the entire sun, that'd be at least 10 trillion times the current global power consumption. And stars are just sitting there, giving off all this energy. Dyson spheres are the obvious thing to do for any advanced civilization, and that's why I think it's not crazy. If you have the technology to harvest the energy of a star, it would be crazy not to do it. Sure, building a Dyson sphere would require a lot of material. It'd require entire planets or multiple moons to build them. The sheer scale of the engineering feat is mind-boggling, but leaving aside the giant size, it's really a straightforward idea. I believe that any advanced civilization would go for something like a Dyson sphere, so if you want to know if there's intelligent life out there, it's the thing that you want to look for. And yes, I strongly believe that there is intelligent life out there, and it's almost certainly much more advanced than we are. You see, our sun is what's called a third-generation star. The first stars were born 13 billion years ago. Our sun is only about 4 billion years old. There have been planets in this universe that are hospitable for life in some form for billions of years. Now imagine a civilization that has progressed its technology for that long. Billions of years. They could have populated entire galaxies by now. Why haven't we heard of them? I think it's quite simple. We haven't developed the technology they use to communicate. Why aren't they contacting us? I think it's because life isn't rare. It's actually quite common, and we're just completely uninteresting. It's like you don't care what microbes are in your backyard. Yes, maybe there are actually some specimens among them that no biologist has ever classified, and yes, maybe some biologists would be interested in that. But let's be honest, most of us don't care about the exact classification of microbes. I think that for aliens, it's kind of like that. We're just another backyard variety, and a pretty stupid one in addition, seeing the problems we're causing ourselves. Have they been here? Did the aliens maybe send some of those UFOs that are no longer called UFOs because renaming things is what we call progress on our planet? Well, maybe they have been here, but I can't think of a good reason why they'd send us any flying objects into the atmosphere, and certainly not why these objects would be just about detectable with our technology, but then not quite. That doesn't make any sense. And I'm not sure, honestly, it's a good idea for us to send messages out into space and beg for attention, because maybe someone takes a liking to our planet. But most of the time, I think that we stand more to lose than gain from finding extraterrestrial life. It could solve a lot of problems very quickly. But until aliens come to rescue us, better keep on dusting those solar panels. I recently read on the BBC website that quantum physics could revolutionize everything. You know what? It won't. But of course you knew this already. I've been thinking, we need a quantum bullshit guide for rich people. Imagine you have a few $1 billion lying around and are looking for a good way to invest them. I mean, who doesn't have that problem? What do you need to watch out for? Let's have a look. This video comes with a quiz that lets you check how much you remember. I found that there are 3 different types of quantum bullshit. Exaggerating how wide the impact will be, that is, how many areas will be affected, how fast the technology will be ready, and how much of a difference it'll make. I want to give you some examples for those, but first some quantum vocabulary. Most importantly, we have quantum computers. Those use quantum bits, qubits, to perform calculations by executing algorithms. The reason this might be useful is that they can, theoretically, do some calculations much faster than conventional computers. This is called quantum advantage. This brings us to the first bullshit: wide impact. Quantum computers are and will remain special purpose machines. There are few mathematical problems for the solution of which a quantum advantage has been demonstrated. They also don't output large amounts of data. They just output one measurement outcome. This already tells you that any application that requires outputting vast amounts of data, like say videos or simulations like a weather forecast, is not the kind of thing you'd put on a quantum computer. And quantum computers must be treated with a lot of care, because otherwise that'll disturb the computation. It's not like one day we'll all have quantum computers in our phones. Quantum computers will be kept in very carefully isolated places and accessed through the cloud, which is already the case for some small systems. So the first red flag for any article about quantum computing is talking of an industrial revolution or something that'll change the world. Quantum computers are interesting, all right, but they'll be niche applications. Besides quantum computers, we have quantum procrastinators, which are startups that postpone their targets. I have a feeling we're going to see some quantum procrastinators in the near future, like IonQ that wrote in 2020 they'd have broad quantum advantage in 2025, and PsiQuantum that expects commercial quantum computers also by 2025. And that brings me to the second bullshit point: how fast it'll come. A lot of startups say they have some type of qubit and they know how to control it. But that isn't the difficult part. The difficult part is to put these qubits together and still be able to control them. I haven't seen much progress on this for several years now. Estimates say we'll need about 1 million qubits with low error and good control. The problem there isn't the number of qubits, but the error and the control. A particularly crazy example of a bullshit headline is this one, which came out of the University of Basel 2 weeks ago. The title said, "Experiment opens doors for millions of of qubits on one chip. If you look at the paper, it's about 2 qubits. This is like saying my dog jumped 2 meters, so he could jump 2 kilometers. I made a joke about this on Twitter, and interestingly enough, they changed the title. And then let me get to the third point, how much of a difference it'll make. The BBC article is a good example. It's not about quantum computing, but about quantum sensing. That's precise measurements with quantum effects. In particular, the people that the article is about are making precise measurements of magnetic fields. That's going to be useful in some fields where you have time and need exact information about the composition of a sample. But it'll not revolutionize the world. Yes, you can make some measurements more precise with quantum something, but in many everyday circumstances, the increase in precision will not be worth the extra trouble. Other examples are using entangled light for making a better LiDAR. Theoretically interesting, practically not so much. Another example is this quantum navigator that uses quantum effects to measure acceleration very precisely, and that allows you to track position without relying on GPS. Again, cool technology, yes, and it has its uses, yes, but it's a huge and impractical device that'll not revolutionize the world. You see, eventually the question of quantum advantage isn't whether you can do something better, but whether that improvement is large enough to be worth the money. Take, for example, the most often used example application for quantum computers, that's breaking certain encryption protocols. But who's the market? Will Jenny from next door suddenly develop a need to factorize 64-bit integers? Probably not. The market is intelligence organizations, governments, and some shady people who you want nothing to do with. And once they've decoded their stuff, that's the end of that market. In other areas like quantum chemistry, they're using machine learning, and maybe that'll just be good enough already. In logistics, often the issue isn't that a company can't compute a particularly optimal solution, it's that they can't or won't implement it. I mean, think of airlines. We know that plane boarding isn't optimal, that ticket pricing isn't optimal, that plane logistics and scheduling isn't optimal, but we don't need a quantum computer to confirm that. So what do we have in summary? To make sense of quantum bullshit, keep in mind it won't affect as many industries as they say, the difference won't be as large as they say, and it'll take longer than they say. If you're looking for something else to do with all your billions, check out my Patreon. Today I want to talk about a peculiar case of, let me call it, amateur physics that's recently attracted a lot of public attention. It's some ideas put forward by Terrence Howard, an American actor who has his own theory of everything that he thinks improves physics. Now, there are thousands of people with theories of something that aren't good for anything, and normally I don't talk about that. I make an exception in this case because Joe Rogan spread these ideas on his podcast, and a lot of people seem to think that physicists must pay attention to actors who want to improve physics. Well, I'm happy to help. So let's have a look. I don't have time to listen to 3-hour podcasts, and if I did, I sure as hell wouldn't listen to some actor go on about his theory of everything. But I saw that he has a book of sorts, and I like books. So I had a look at this, and I'm now at least as qualified to comment on his ideas as he is to comment on modern physics. Terrence Howard's key fundamental insight, the basis of his new theory of everything, is that 1 times 1 equals 2. Just in case you had any doubts about it, 1 times 1 equals 1. That's not a matter of opinion, it's not even a matter of science, it's a matter of definition. The mathematical operation that we call multiplication and the number that we call 1 are defined so that any number multiplied by 1 gives the same number. Consequently, 1 times 1 equals 1. We define multiplication this way just because it's useful. You see, if you have only addition and I give you 7 apples, you'd have to go 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 equals 7. The operation of multiplication is a way to simplify this long sequence of addition. We introduce a new symbol, call that times, and write 7 times 1. It means the same thing. Howard goes on to write, in order to multiply something by something else, they must be dimensionally equal. This is not correct. If you multiply one quantity that has units with another quantity that has units, you multiply the units. If I multiply, say, time measured in seconds with a speed in meters per second, I get a length in meters. This is the case for any quantity, but a lot of things that you can mathematically multiply don't serve any purpose, so we don't multiply them. I could, for example, multiply 18 chopsticks with a magnetic field of 2 Tesla. That would give me 36 chopstick Tesla, but just because that mathematically exists doesn't mean it makes any physical sense. But Howard's confusion about multiplication goes so far that he thinks if you multiply a penny with a penny, then, according to the current rules of mathematics and multiplication, that gives you 1 penny. This is not correct. It would give you a penny squared, which isn't a physical thing. But now he has an entire conspiracy theory about how Bank of America miscalculates your pennies. Oh dear. Okay, so he doesn't understand either multiplication or units, which, let me just say, is a bad start for revolutionizing physics. But how does he get from there to rewriting the laws of nature? Well, as I read on, it became apparent that Howard confuses mathematical relations with natural laws. Yes, in physics we formulate the laws of nature in form of mathematical relations, but that doesn't mean any mathematical relation is a law of nature. Since he thinks that something is wrong with 1 times 1 equals 1, and he thinks that multiplication is a law of nature, he now thinks that physics is wrong. He explains the laws of conservation of energy might as well pack up and move away, because how can a something multiplied by nothing cause the something to disappear? Remember, energy cannot be created or destroyed. That's why there is no law of nature that just multiplies energy by 0. A few pages later, he has concluded that all visible things are composed of the properties of light. This is what the equation E equals mc squared is ultimately illustrating, that energy equals mass times the velocity of light squared. All things are light. Unfortunately, this is not correct. This equation doesn't apply to light. You see, the full equation is actually E equals the square root of m squared, c to the 4th, plus the square of the momentum times the 2nd power of the speed of light. If the object you're looking at doesn't move, then the velocity is 0, so the momentum vanishes. That gives you E equals mc squared. But light moves, well, at the speed of light, so the momentum can't vanish. Instead, for light, it's the mass that's 0, so you get E equals P times C. And no, all things cannot be light most trivially because light has no electric charge. On page 102, he then begins a crash course into particle physics and quantum mechanics. That sounds promising, so let's have a look. It's an elaboration based on a lecture about quantum field theory by David Tong, who I'm sure is thrilled to be cited in this groundbreaking work. David is quoted as saying that the idea that the world is made of particles is strictly speaking a lie, because quantum fields are the real building blocks of the universe. Howard seems to think that this is somewhat of a revelation, that the world is made of quantum fields and not of particles. But what can I say? Yes, the standard model of particle physics, which is half a century old, is a quantum field theory. It is, despite its name, not a theory of particles, but of quantum fields. A quantum field, loosely speaking, tells you how many particles of what type are in which place. So even if there's no particle in one place, there's still the field there that tells you that no particle is there. Howard seems to think there's something wrong with it, because because Tom correctly says that the equations can be extremely difficult to solve. So then Howard introduces his new theory, which is that the third power of 1 is the absolute value of pi. And this is the neutral condition of all visible matter. The rest of the book is basically pictures. He does not make a calculation for any measurement result, but complains that, quote, "That's one of the biggest problems in the field of science and mathematics. It goes beyond the fact that it's outrageously cliquish. It's as if they never truly left high school and the silly games of unconscious children pretending to be important adults. In truth, they are just afraid to explore new ideas," end quote. In summary, we have a man who wouldn't pass a primary school maths exam, who thinks that lumping together words and images will revolutionize physics. A man who has zero respect for thousands of years of hard-working mathematicians and scientists whose efforts made it possible that you can see him on a screen and listen to him through a most excellent microphone. A man who belittles generations of physicists who have spent their life to figure out what matter is made of and how electromagnetic radiation propagates and how the universe expands. Achievements that Terence Howard thinks he can improve on by drawing a few lines and squaring pennies. Now look, some people have told me that Terence Howard has a mental health issue, or maybe he's been doing too many drugs, or both. I don't know if that's correct, and I don't want to speculate about it. I don't blame him. If you can make it through school with that significant deficits in basic education, then that's a problem with the educational system. No, I blame Joe Rogan, because Rogan isn't stupid. He believes that his audience is stupid. He believes that his audience is so stupid to think they'll lap up any nonsense he throws at them. Is Rogan right? Well, he certainly knows how to multiply his pennies. Hypersonic weapons have been in the headlines a lot over the past year as Russia, China and the US race to develop the next generation of high-tech missiles. But are these supersonic sensations all hype and less hyper? Here's a quick summary of what you need to know. Hypersonic missiles fly at speeds of at least Mach 5, where Mach 1 is the speed of sound at sea level, that's 343 meters per second. Mach 5 is then 5 times that speed, that's more than 6,000 kilometers per hour. Hypersonic missiles fly below 100 kilometers altitude, that's low for a long-range missile, and they can strike targets thousands of kilometers away within minutes. But the major reason that we are at risk of a new global arms race is not just the speed. It's that these missiles can change direction as they fly, and they're hard to detect. Most currently used long-range missiles are ballistic missiles. You can think of them as dumb missiles, basically. After launch, they just follow a trajectory that's a giant arc. They often go above 4,000 kilometers and then essentially fall back down to hit their targets. Since they go so high where there's no atmosphere, they can actually reach higher speeds than hypersonic missiles, which fly much lower. But since the arcs of ballistic missiles are so long, hypersonics can often reach targets faster despite being slower. These arcs of ballistic missiles, like the blue one here, are quite easy to track and predict by satellites and missile defense systems. Hypersonic missiles, in comparison, fly low within Earth's atmosphere and can avoid radar detection systems, which are limited by the planet's spherical shape. They are also much more mobile than their ballistic counterparts. You can see this in the pink line here. They can be controlled mid-flight, making it much harder for missile defense systems to track them. So far, Russia and China have been the main investors in hypersonic weapons, with the US joining in late. Over the past few years, Russia has developed 3 different hypersonic weapons. First, there's the Avangard, that's Moscow's most impressive/terrifying long-range hypersonic glide vehicle. vehicle. It's launched from a booster rocket, carries a nuclear warhead, and can allegedly reach speeds topping Mach 25. Then there's the Zircon, a more general-use hypersonic cruise missile which can be launched from ships and reaches speeds from Mach 6 to 8. Lastly, the Kinzhal is a maneuverable air-launched hypersonic weapon with a range just below 2,000 kilometers and a top speed of Mach 10. China, meanwhile, has also developed a long-range hypersonic glide vehicle and several other hypersonic weapons, such as the Starry Sky 2, which has powered flight. As for the US, the Department of Defense has lagged slightly behind on hypersonic weapons. The US Air Force has contracted Raytheon to develop a scramjet-powered cruise missile, which they've used all their creative power to name the Hypersonic Attack Cruise Missile. Another hypersonic missile program of the US military, the Air-Launched Rapid Response Weapon, was cancelled in late 2023 after several tests had failed. But hypersonic weapons have been criticized by people not in the military for being expensive and useless. For one thing, in the past decades, engineers have made ballistic missiles smarter by finding ways to change their paths upon re-entry into the atmosphere. This also confuses defense systems, and the advantage of hypersonics becomes less clear. Then there's the question of whether the theoretical advantage of hypersonics will actually create good outcomes on the battlefield. Maneuverability sounds nice on paper, but in practice it requires energy and creates a lot of drag. This means that while hypersonic weapons technically can fly around in crazy patterns, doing that reduces their speed and range. Another issue is that traveling at hypersonic speeds through the atmosphere creates a lot of heat. That's basically a very bright infrared signal. Indeed, multiple Russian hypersonic weapons have reportedly been shot down by US Patriot air defense systems deployed in Ukraine, meaning the cutting-edge tech is being beaten in real life by an air defense system introduced in the 1980s. It's for those reasons that critics, including scientists at the RAND Corporation, MIT, and the Union of Concerned Scientists, have argued that the new technology is not worth the money it costs. They say that current ballistic missile technologies can be upgraded to match some characteristics of hypersonic weapons. But others within the military-industrial complex have argued that it's necessary to keep up with adversaries and that the raw striking speed of hypersonics is unmatchable. Either way, militaries around the globe have poured billions of dollars into developing their own hypersonic weapons. In 2023, the Pentagon allocated $4.7 billion to hypersonic research. To me, that sounds like a lot of money to spend on blowing things up, but if it helps us annihilate each other a few minutes faster, I'm sure it's worth it. Thanks for watching. See you tomorrow.